Hello, everyone, and welcome to this webinar where we will be talking about the impacts of wildfires on solar generation, electricity prices, and operating reserves, and the project that we've been doing for last couple of years, and we will share our findings from that with you all. So you can currently see on the screen the project team, which includes Manojit Sengupta, who is a solar energy expert. And in addition to me, we have Meng Kai, who is a power systems analyst at NREL, Jinan Lin, who did work on atmospheric and solar modeling, and then Yimin Zhang. So today we will hear from Meng Kai and Jinan Lin, in addition to me, who both will talk about our findings from this project. Next slide, please. So just an overview of the agenda. I will introduce the project and then hand it over to Chinan, who will talk about development of wildfire scenarios and what is the impact that we saw of wildfires on solar radiation. And then we'll pass it on to Meng Kai, who will talk about market impact analysis, both real world and real world analysis of historical data, as well as future simulations. And then we'll conclude with some findings from this work and what we think needs to be done next. Slide, please. So just to give you a brief introduction, here we can see what was observed in California during 2020 wildfires. So if you focus on the figure on right, you see that the California wildfires as they progressed, caused a significant deterioration of solar generation. So if you focus on the figure going from left, which is early July, to the right, rightmost corner, which is late September, you can see that solar generation decreases quite a lot by almost more than 50%. And that coincides with what PM 2.5 concentrations were observed in California. So this clearly points to that wildfires release smoke and have a significant impact on solar generation. And this is in addition to any anthropogenic emissions. Anthropogenic emissions caused PM 2.5 can also reduce the solar generation, but wildfire released smoke almost always have an outsized impact. We also know that based on several recent studies that the wildfire activities has been going up. In fact, some of the statistics indicate that the wildfire burn area in California has increased by almost 400% between 1970s to late last decade. So this all points to this important topic that we must consider as we move towards a clean energy transition that will rely on solar energy quite a bit. Next slide, please. So we saw that wildfire activity has been growing quite a lot, and the top right graphic here shows that the wildfire burn area has been consistently increasing. And 2020 was a very unique year in several aspects where it broke all the records. At the same time, wildfires, even though they are limited in the area where they burn, the smoke can be transported over long distances, and there can be a significant impact at large distances away from the source where the emissions are occurring. Now, we have one trend where the fires are increasing, but at the same time, a large number of states are that have abundance of solar resources have continued to lead in solar deployment. In fact, California, Nevada, and many of the Western states lead in terms of the both fire record as well as the solar resource integration. So this again highlights to the fact that we really need to study this problem in detail. Next slide, please. So by now you have some idea of where we are heading, but just to give you a brief of why we selected which particular region we went ahead with this in this analysis. So we focus on California because it leads solar integration in the US. And as you can see on this bar chart on right, that solar PV is expected to go quite significantly, going up to like 35–40% in late 2040 and almost 50%, half of the electricity generation coming from solar PV. At the same time, a lot of studies have indicated that the wildfires will continue to grow in future years under different climate scenarios. So that's all highlights to the fact that we need to understand how wildfires can impact power systems operation in California. Next slide, please. So to give you a broad overview of different project activities, so our objective here is to provide a screening level analysis to quantify impacts of wildfires in California. And we will focus on what impact wildfires have on solar generation, what impact they have on operating reserves, as well as on electricity prices. So the three boxes corresponds to three broad set of activities that we carried out, which included collection of wildfire data, making sure that the data sets that we are using, specifically NSRDB data set, does work well during extreme fire seasons. And then we focus on three different wildfire scenarios under which we study the impact on power system. Those are no wildfire scenario, essentially only considering any impact from anthropogenic emissions. Then 2020 wildfires, we take the historic existing data from 2020 California fires, and then we create a synthetic enhanced wildfire scenario to look at the impact what if 2020 wildfires, there was a year when we experienced wildfires which are much more than 2020. And then on the power sector side, we do two different analyses. First, looking at historical data and doing a data mining of that to see if there are any signals in the historical data that can show the impact on operating reserves and electricity prices. And then we consider a future analysis where we look at what if the solar infrastructure grows, and at the same time, let's say a 2020 wildfire were to recur or an enhanced wildfire to occur in that year. Now, I should mention that our analysis here only focuses on the impact wildfires have on solar generation. There could be additional impacts there, which could be through damages to transmission lines or substations or power plants, which can have additional impacts on all of the things that we are considering in this study, but those are excluded from this analysis. Next slide, please. Now, this here gives a broad overview of the methodology that we adopt. So we start with the three scenarios and create emissions inventory for each of the scenario. Then we use a state of the science atmospheric model called WRF-Chem to study the impacts of smoke from different scenarios on aerosol optical depth, which is then passed on to quantify the impact on solar radiation, specifically looking at the global horizontal irradiance and direct normal irradiance. At the same time, we collect data set on projected growth of solar generation, looking at the mid-century, which is kind of the time horizon that we are considering here. And also including some findings from the historical data mining exercise, specifically related to electricity prices and reserve margins. And we bring all of those activities from atmospheric modeling domain and power sector analysis domain to eventually study the impacts of large wildfires, 2020 wildfire or enhanced wildfires on photovoltaic generation, operating reserves, and prices. So next slide, please. So that was an overview of what we are doing and why we are doing and how we are doing. Now we'll dive into more detail here. First talking about how we develop the wildfire scenarios and what's the impact on solar resources, solar radiation. For that, I will hand it over to Chinan Lin now.
Thank you, Vikram. Hi, I'm Chinan from Pennsylvania, and I will talk about the development of the wildfire scenarios. Next slide, please. So to determine the impact of the changed wildfire activity for the intense wildfire scenario, we conducted a comprehensive literature review, and the reported projected increase of the fire activity are shown in the figure below. So in this study, we are targeting 2050, and the reported projected increase of the fire matrix ranges from 2% to 240%, with the majority ranging from 40 to 100%. And this large variation is possibly due to the selection of the future climate scenarios, climate models, and models, fire prediction models, and the focus area and the period. However, since the goal of this project is not to predict the fire activity for the future climate, so here we selected the median value, which is 165% of the projected increase in area burned for the following analysis. Next slide, please. Then to create the AOD and the solar radiation data set, we use the Wolfram model with the fire emission fin, to which we apply the relative increase of the fire matrix to represent the impact of the enhanced wildfire activity on the smoke aerosol in terms of the magnitude and the spatial distribution. And since in this study we are focusing the wildfire activity in 2020, so I would like to mention that we only intensify the wildfire area burned, but the location and the period of the wildfires remain the same as that in 2020. So in this study, we conduct a 5-month simulation from June to October at 12 km resolution. So with the created LDR set, we then use the NREL's physical solar model and use the same model configuration used to simulate the SRDB dataset, and it can provide the solar radiation data at a high spatial and a temporal resolution. Then we also do the evaluation of the SRDB dataset for the high fire period, and it shows that the correlation of LD and DNR are high. So this indicates that the SRDB will capture the variation of the LD and the solar radiation data. Next slide, please. So to wrap up the development of the wildfire scenario, so we created the LD data set for 3 wildfire scenario, and the monthly LD map is shown in the figure in the right here. So as you can see that in 2020 wildfire and the enhanced wildfire scenario, elevated LD can be found over the northern and the central California. But in the enhanced wildfire scenario, we can find the LD magnitude is slightly larger than the 2020 wildfire scenario. So with this LD asset, we then conduct the simulation for the solar radiation. Next slide, please. And then I will talk about the impact of the wildfire on the solar radiation. Next slide, please. So first, we investigate the wildfire cause changes in LD and the solar radiation by comparing the 2020 wildfire and the no wildfire scenario. So the left figure shows the LD and the DNI differences between these two scenarios for each month. And as you can see that the wildfire can lead to the increase of LD by up to 2 over northern and the central California. And this will lead to the reduction of the DNI by up to 200 watts per meter square. Then to quantify the wildfire impact, the box plot shows that the wildfire can lead to the increase of the AOD by a factor of 2 to 8, and this will lead to the reduction of the DNI by about 9% to 23% in the 2020 wildfire scenario. Next slide, please. And then move on the impact of the enhanced wildfire scenario. So the left figure also shows the AOD and the DNI differences between the enhanced wildfire and the 2020 wildfire scenario. So the enhanced wildfire activity can lead to the increase of LD by about 0.5 to 0.8 over the northern and the central California, and this will lead to the reduction of the DNI by about 100 watts per meter square. And this is because the smoke aerosol emitted by the wildfire can be further transported by the wind from the source region to the downwind region. So, and you can also see that the reduction impact on the DNI can be comparable over the source region and the downwind region. Then the right figure just summarizes the wildfire impact for the 3 wildfire scenario. As you can see that the enhanced wildfire can lead to the increase of the LD by a factor of 4 to 10 in the enhanced wildfire scenario, and this will lead to the reduction of DNI by about 11 to 26%. And we can also find that the differences between the 2020 wildfire and the enhanced wildfire scenario is not that large. And this is because the 2020 wildfire activity is already very strong. So we do not see a very significant increase on the impact for the enhanced wildfire scenario. Next slide, please. However, because we know that the smoke aerosol can be transported by the wind, and it could have a very large temporal and spatial variation. So here we focus on the smaller period and the domain. And here we look at the 5 days in September, and thus we selected one near source region, the Greater Bay Area, and one downwind region, the Los Angeles metro area. And as you can see in the plot here, we can find the impact of the enhanced wildfire is intensified, and it can lead to the daily reduction of the DNI by up to 60% over both the source region and the downwind region. So we may expect that the wildfire impact could be even stronger if we focus on the shorter period, like the hourly or the minutes, and this sudden reduction, large reduction of the source resource could lead to the uncertainty and the vulnerability to the grid stability and the solar market. So this just read up the analysis of the impact on the solar resource. Then I will pass to Meng for the marketing analysis.
Thank you, Jing'an. So hello everyone, my name is Meng Cai. I'm a researcher with the Power System Engineering Center at NREL. In the following slides, I will be discussing the key findings that we got from our wildfire market analysis. I will start with a real-world data mining based study and then talks about a simulation-based study. Next slide, please. So for the real-world data mining study, the availability of the real-world data is key. And here in the 3 tables, we summarize all the wildfire relevant and market relevant data, including the wildfire records provided by multiple wildfire agencies, the Clear Sky GHI provided by an SRDB, as well as 4 types of market operating data fetched from CAISO or ACCESS database. Note that the Clear Sky GHI data were collected as an indirect measure of wildfire to compensate the low temperature, temporal and spatial resolution of the wildfire record. And given the availability of the real-world data at different resolution, we decide to conduct the Wildfire-PV generation and the reserve impact analysis at the system level with the monthly resolution, and to perform the wildfire price impact analysis at both the system level and the zone level with the monthly and the daily resolution. To facilitate the monthly analysis, we first identified months with significant wildfire impact based on the wildfire record data. What we did is we calculate the system-wide monthly total burning areas based on by evenly distributing the burn area of each wildfire event between the start date and end date. And we then select 0.2 milli acres as the threshold to filter those months with total burning area existing 0.2 milli acres as shown by the table. And our result shows that 2019 and 2020 stands out as the least and the most significant fire years and the occurrence of the wildfires are more profound in the later part of the year for 2017, 2018, and 2020. Next slide, please. So here presents the analysis on the wildfire PV generation impact. We compare the monthly PV generation profiles as indicated by the area plot against a rescaled 2019 baselines as indicated by the green curves between 2017 to 2020. And the bar plots on the bottom indicates the difference between the two. Note that 2019 is selected as a baseline given its lowest wildfire intensity. And also we use the purple dashed line to frame those months with the burning area being greater than 0.2 million acres. Our result shows that across the years, 2020 has the most significant PV generation reductions. And within each year, the months with greater wildfire impact has greater PV generation reductions compared to its 2019 baseline. And our finding also shows that the monthly PV generation reduction can go as high as 10% as observed in September 2020. Next slide, please. A similar analysis has been performed on the Wildfire-Reserve impact. Here we compare the day-ahead reserve minimum requirement versus the real-time online operating reserve. And with the green bars on the bottom indicates the difference between the two. Again, the purple dash line indicates the months with greater wildfire impact. And our result shows that across year 2020 and 2019 had the highest and the lowest demand for system reserve, and which within each year, the months with greater wildfire impact had on average 50% less operating reserve surplus than the remaining months in the year. Next slide, please. Moving on to the wildfire price impact, we start this analysis by comparing the ratio between monthly and yearly average market price on the left and the ratio between monthly and the yearly market price variation on the right. According to the figure on the left, we show that whereas 2017, 2018, and 2020, which are the years with greater area burned, witnessed a rise of price in the second half of the year, which coincide with the period with greater wildfire influence. 2019 is an exception, which is the year with lower area burned. And among the 12 months with a burning area existing 0.2 million acres, 11 of them contributing to greater than average market price, indicate a correlation between the wildfire and the price increase. Though according to the figure on the right, we don't see a strong correlation being indicated by the real world market price variation. Next slide, please. So the market, the Wi-Fi market impact analysis we have discussed so far are purely based on the wildfire record data, which have a low resolution and can provide us limited insight. Therefore, we further collected the GHI solid radiance data from NSRDB and create a GHI-based wildfire index to measure the wildfire intensity by calculating the difference between the clear sky GHI under the 2020 wildfire and the non-wildfire scenarios, which can provide us higher flexibility to decide the level of resolution we want to look into. And the figure on the right compares the total burning area, daily burning area we calculate based on the wildfire record versus the GHI-based wildfire index. for their day-to-day variations. And we see similar patterns between the two, as both of the curve kind of reach their peak value in the mid-August and reduced to its median value starting from mid-September. Indicate that this wildfire index can serve as a great indicator for the wildfire intensity, while providing more details about the day-to-day variation compared to the wildfire record. Next slide, please. Based on this GHI-based wildfire index, we further calculate the Pearson correlation between the daily averaged price and the daily averaged wildfire index. And we using the zoom partitions as showing in the right map. And our result shows that the correlation between solar irradiance and the market price decreased gradually from August to October as the grid become less dependent on solar generation. And in the months with the highest correlation, which is August 2020, zone with greater solar capacity, such as Southern Central Valley, LA Metro, and Eastern California, the correlation between the solar irradiance and the market price are stronger. Next slide, please. So this wrap up our findings from the real-world database study. And we do notice some limitations of this work, including the low spatial and the temporal resolution of the wildfire record, the uncontrollability of other factors that influence the market price other than the wildfire, and also the lack of true non-wildfire market operating data baseline. Given that, we further conduct a simulation-based study, which provide us three advantages. First is that the simulation data can be obtained at arbitrary spatial and temporal resolution, provide a high flexibility of the analysis. And the second, it allows us to fix the other influential factors during a comparative study. And thirdly, it allows us to analyze how wildfire impact the market with the growing wildfire intensity and the PV penetration in the future. Next slide, please. Next slide. Thanks. So we conduct our market simulation using an industrial standard tool called PLEXOS. And we used a PLEXOS model developed under an existing NREL project that covers the entire footprint of WAC system. Three NREL in-house tools, READ, SCRIP, and DGen, has been used to jointly decide the least cost power sector investment decision for the utility scale PV, as well as the market potential for the distributed PV. And here we created two infrastructure years to reflect the solar penetration level in California at 32% and 36%, reflecting the situation in 2024 and 2036. And the two maps on the right shows the details about how the utility scale and distributed PV installation capacity distributed across the California in two infrastructure year. Next slide, please. Based on the PV metadata we got from the we described from the previous slides, we further leverage the NREL System Advisor Model SAM to translate the meteorology profiles into the PV generation profiles on the different wildfire scenarios. And in order to capture the correlation between the system demand and the solar generations governed by the underlying weather condition in 2020, we further collect the BA level demand profiles based from the EIA 930 database and apply the projection factors got from the EIA annual energy outlooks to reflect the demand growth from 2020 to 2024 and 2036. And since wind generation is not a focus of this study, we remain using the wind profile from the existing model, which are created based on the 2012 weather data. Next slide, please. Another key input for the PLEXOS model is the reserve requirement, which in our study are defined to cover the uncertainty in wind, solar, and the load. And the uncertainty for wind and solar are estimated based on 30 minutes ahead forecast and the 90% confidence intervals of the forecast error. And for the solar, particularly, we apply the solar power index-based persistent forecasting model to evaluate the forecasting error. Next slide, please. So the simulated Wildfire-PV generation impacts are presented first. So here the dotted curve in these two figures compares the monthly PV generation profiles on the three wildfire scenario, with the percentage PV generation reduction being highlighted by the bar plot, the blue and orange bar plots on the bottom. The absolute PV generation reductions can also be found in the table below. And our result indicates that 2020 wildfire could result in a decrease of up to 7.7 monthly PV generation reductions, with the September being the highest, and the additional 0.4% and 1.3% reductions can be further contributed by the wildfire enhancement and the PV generation growth. And we also calculate the daily result and find that the daily PV generation reduction can go up to 19% based on our result. Next slide, please. So next, we will analyze the Wildfire-Reserve impact. So the area plot on the left compares the 90% confidence intervals for the PV forecasting error on the three wildfire scenarios. We can see that as the wildfire intensity become more severe, the confidence intervals become wider, indicate a higher uncertainty of the PV generations. And by using the 95th percentiles to define the regulation app requirement in our model, we further calculate the monthly system-wide PV reserve requirement as shown by the right two bar plots for under 2 infrastructure years. And we see that the 2020 wildfire and the enhanced wildfire could lead to an increase in the PV reserve requirement by up to 53% and 64%. Next slide, please. Now moving on to the wildfire price impact analysis. Here we first compare the statistics of the energy price distribution in the 2 infrastructure year on the 3 wildfire scenarios by calculating the median, standard deviation, and also the percentage of time when the price going above $100 per megawatt. And the results are showing in the table on the left. We show that the wildfire could potentially raise the market price and introducing more price volatility and cause more price spike. And compared to the raising the market price on average, we see that the wildfire has a stronger influence on raising the price volatility. And also, I want to point out that we see a strong standard deviation in the year of 2036. And I think the reason might be because we consider higher PV renewable generation in the year of 2036 that will result in a higher price volatility. Yeah. Next slide, please. So the next slides analyze how the wildfire location influence the wildfire's impact to the market price. For doing that, we have created two clear sky GHI-based index that calculates the system level wildfire impact using two different approach. The average GHI difference simply calculates simply average the difference between the clear sky GHI between the non-wildfire scenario and the 2020 wildfire scenario, whereas the weighted GHI difference calculates the difference weighted by the capacity of the PV installation at different location. By comparing the difference between the two, we are able to capture the difference in terms of how the wildfire are located with respect to the PV installation location. And in the three plots in the middle, we shows the day-to-day variation for the system load, the average wildfire intensity, the weighted wildfire intensity, as well as the energy price into the wildfire scenarios. And based on which we select 2 days with similar level of system load and the similar level of average wildfire intensity, but different weighted wildfire intensity. The 4 plot on the top shows the distribution of the price change between the two scenarios, as well as the wildfire intensity distribution across California. We can see that whereas these two days have similar average wildfire intensity system-wide, the wildfire are distributed at different locations, whereas the day on the left have more severe wildfire in the north area. The wildfire are concentrated more on the southern area for the day on the right. And we show that results in different price change patterns. The days with more wildfire that located closer to the area with higher PV installation capacity, the price change are more significant. Next slide, please. Based on the system level wildfire index that we introduced in the previous slides, we further calculate the wildfire price correlation, both at the system level and the node level. And according to our results, stronger correlation between wildfire and the price are observed in the year with higher PV penetration, which is 2036. And when the weighted wildfire intensity index is applied, and we also see that more spread out influence of the wildfire price are observed when the PV penetration increase. Next slide, please. So this wraps up our discussion for the simulation-based study. The next slide presents the conclusions, the key takeaways from our study. Next slide, please. So we see that 2020 wildfire could result in 7.7 and 57 monthly PV generation reduction and the monthly operating reserve requirement increase. And with the growing wildfire concern and the growing PV penetration in the future, this influence could goes up to 9% and 64%. And we also show that the node with greater wildfire price impact are the nodes with greater PV installation capacity instead of the nodes that is closer to the wildfire centroid. In addition to that, we also see that with the trend of growing PV installation, it is expected that the wildfire impact on market price will potentially increase and become more widespread. And also, as discussed both by me and Qing An, the wildfire scenario in 2020 is already very strong. So no significant actual market impact has been observed after we consider the wildfire enhancements. And we also think that this futuristic analysis could serve as a valuable information for policymakers, business, and the stakeholder to facilitate the development of their strategy to mitigate the risk and enhance the resilience of our power grid. Yeah, in terms of the future work, so first of all, we will consider more realistic profiles for other sectors, including wind, thermal outage, and the hydro power plants to provide a more comprehensive analysis. And for now, the production costs that we applied in this study only support real-time simulation, which means no day-ahead scheduling and the low solar wind forecast has been considered. So we plan to add a day-ahead to real-time simulation in the future to analyze how wildfire influence the system preparedness and the day-ahead to real-time price convergence. And lastly, we think to investigate how the different design of operating reserve requirements could help reduce the real-time risk. For example, the price spike and the reserve shortage introduced by the wildfire could be another interesting topic. So with that, I will hand over the floor to Aaron for the Q&A.
Okay. Thank you. My name is Aaron. I'm with the Sensing and Predictive Analytics group at NREL, and I will be moderating the Q&A. So we have a few questions. So the first question is for Magman. Are we only using utility scale PV, or do we include rooftop PV? I think this came maybe before your presentation, but I think maybe elaborate on the UPV and DPV.
Thank you for the question. So we did consider both the utility scale PV and the distributed PV as we present in the slide that shows how we prepare the PLEXOS model for conducting the market simulation.
Thank you. The next question is to Manojit and maybe Vikram, if you can add too. So how do we account for wildfires in long-term PV energy prediction, which use historical TMY weather data sets? So do we need to do something in the weather data in the TMY data set itself to account for that, or additional loss factor needs to be added in the model that is presented to include for people who use TMY data set?
Yeah, I don't think we can really account for wildfire in TMY because wildfires always occur at specific weather situations, and TMYs don't necessarily represent those extreme weather situations. As you remember, if you remember, TMYs are generally a median month collection from multiple years. So extreme events which will cause such serious wildfires like we saw in 2020 will probably not even show up in a TMY. So I don't think that would be a possibility. We would probably have to use the full time series data set instead of a TMY for this purpose. It's extremely challenging to represent wildfires and identify, especially when wildfires will happen, even if you have multiple years of data. But there are definitely correlation studies which show when wildfire events happen, and there are correlations with temperature and humidity and other factors. There's also the biomass loading. So wildfire is very complex. It's not straightforward way. There's not a straightforward way to use a TMY data set. Vikram, you have anything to add? But
thanks, Manojit. Yeah, that was a great explanation. I'll just add one thing. In this specific analysis, even though like we are relying on 2020, we use the same 2020 locations for the fires in future years. So essentially, in a way, we are considering that our meteorological data that affects dispersion of wildfire smoke is frozen in time. So now the fires in future years may look different. They can occur at different locations, and then that can also affect how the plume disperses once released in the atmosphere. So yeah, that's a very challenging topic, and especially considering like how what kind of impacts fires have on TMY, that remains challenging, and I think needs to be considered in the future.
Okay, thank you guys. And the next question is, I think maybe let me extend that one a little bit more. The question that came was the impacts of soiling due to pollution. Is that considered in the study? And there was another question that Vikram, you answered already on the load change too, due to cooling effect from the wildfire too. And maybe you can kind of aggregate those two questions, answer if you can.
So let me quickly say, so the load change, I think Meng can answer the impact of load on wildfires. Like if you have this pollution, less or radiation, so there is a change in the load. Is there a change in the load? So I think Meng can answer that question. And what is the other one here?
They are related. The other one.
I can jump in for the question regarding the load profile. So, sorry, let me turn on the camera. So that's a great question. So in our study, we do not consider the influence on the wildfire's influence to the load, but in order to, but we have 3 different wildfire scenarios. So we're trying to match the load at least with the 2020 wildfire scenario by getting the historical load data from the EIA 930 database. However, we do not create the new load profile to represent the load scenarios under the non-wildfire and the enhanced wildfire scenario. So I think a future work could also to consider how the wildfire intensity would impact the load. Yeah.
And just I try to answer another. I don't want. So for the other question on soiling, no, we did not consider additional losses in generation from soiling. Basically because of enhanced smoke and aerosols. I think in that way, you can say the study is conservative. It still allows for more generation. So what we can say is that it probably might be worse. The situation might be worse than what we currently presented. So no, we did not consider soiling because that's so uncertain that it'd be extremely challenging to do it. The study was a very short study, a period 1.5 years. But again, that can be considered in a more detailed study in the future. Aaron.
Okay, thank you, Manju. Thank you all. So the next question is maybe Vikram, you can start then, or manage it. You guys can answer it. On mitigation strategies to wildfires, is fuel management, example, via controlled burns, usually much smaller in intensity and regional extent. Would your model still be able to answer questions of PV pricing impacts of controlled burns?
Yeah, so when thinking of control burns, I think we need to think from two different aspects. One is control burns as a fuel management strategies do reduce the possibilities of large wildfires. But at the same time, controlled burns or prescribed fires, as they are called, can also occur at different times of the year. Usually, like if we think of the Western US, these controlled burns occur in late winter months. So usually, late fall months. So that is around September or October, when there is, or maybe even November. So at that time, there is relatively less production from solar resources. So as we move to other parts of the US, the time at which these prescribed fires are often carried out, that again changes. Like in Eastern US, that's in April or March months. So there is an impact on availability of the resources because of that. But yes, I guess there will be impact on PV generation, and the similar methodologies can be applied to assess the impact of those controlled burns. But those controlled burns are usually much small in size, and they likely have less impact on reducing the solar generation, and thus likely the impact. I don't want to say that the impact will be small on the prices, but we can apply the similar methodologies to assess that.
So I can add a little bit to that. One thing we've been finding is that if we know when there's going to be a fire, you probably plan for it. So you could plan additional reserves. Most of this, especially what we observed, at least from the minimum data we had, when analysis found that when the fire first happens, the prices rise because you're not prepared as much with your reserves. But if for the next day, you know that you're going to have lower resources, and if there's enough reserves available, you already plan them online. So if there's controlled burns, you probably have the information which you could plan on so that you can have additional reserves online to meet the reduced generation needs. So it's extremely complex. It's like fires occur, we don't know, and then we basically have scrambled to put more reserves online in the immediate term, and then if you have sufficient reserves in the backup, then you can plan on it, because you know that the fire is going to burn, and you get reports of where the fire is going, or the next day's weather, and all of that information, which kind of helps in reserve planning. I don't know, that's much my thing. If you have anything to add, otherwise, Aaron, we can move to the next question.
No, I think that covers all. Thank you.
Okay, I think the next question, I have one question. I think maybe Manojit or Chinan can answer. From a cause and effects perspective, the change in climate, as we know, causes the extreme weather conditions like wildfire. On the other hand, increase in temporal and spatial resolution of these extreme conditions does those affect the thermodynamics of the atmosphere, and then affect the future climates?
So if answer that question, so Aaron, if I understand your question, that in future how wildfires will behave.
The impact on the thermodynamics of the atmosphere.
Wildfires are in the whole context is localized and short-lived. They're not like worldwide or something which will have a big impact. So wildfires are happen, the smokes disperse, and it's all, there's no long-term impact on the thermodynamics of the climate. Weather-wise, it does have an impact, but not on climate. But I think we're over time, Aaron. So Daniela, over to you.
Yes, thank you. We appreciate everyone submitting questions to this Q&A. We answered as many as we could, but if you have any other questions, you can reach out to Manajit or Vikram, and I will be sending their email addresses along in the follow-up email, along with a link to the recording of this webinar. So thank you all for joining us. We hope you join us for future sessions, and have a wonderful rest of your week.